So let's take a look at this experiment and see what we can read from it. So what happens is they have a cathode, and what this cathode does is heat it up, and when it's heated up, it's producing a whole bunch of electrons. Now remember, electrons are going to want to attract towards this positive plate. So we've got a mesh grid, which means most of the electrons should be able to make it through. And not only do they make it through, they're going to accelerate towards the plate. They're going to be going so fast that even though the collecting plate here is negative, it's not going to be enough room for it to slow down. And as a result, the electrons were going to hit this plate and then follow down into the wire and then be picked up by this ammeter here. What we would expect in this case is as we increase the potential difference, or the voltage, we would expect more electrons to make it through here and increase the current. So what we expected with this graph is to see something like this. This is what's expected. And when this tube was completely empty, that's exactly what we saw. So the next thing they did was they filled it full of mercury vapor. Why'd they pick mercury vapor? Well, remember, mercury at room temperature is a liquid, so it's really easy to get into a gaseous form. And it's also a fairly dense atom, and because it's a dense atom, there's more likely for collisions to occur. So what they did, if I can erase this, is they filled it full of mercury vapor. And what they found is when they got to specific voltages, some funny things were happening. So at lower voltages, it was following the curve, and all of a sudden we saw a dramatic drop down here. And then we saw two smaller dips before seeing one more giant dip down here. So what's happening here? Well, what they found is that at lower energy, the electrons in here would collide with the mercury vapors and they would bounce right off. They would be perfectly elastic collisions. And that's to be expected. If you remember grade 11 chemistry, where we talk about the ideal gas, is that they're perfectly elastic collisions. But what they found is at very specific voltages, the first one here being 4.9, is that it wasn't an elastic collision. It was inelastic. What we mean by that is that the electron lost all its energy and transferred it to the mercury. So what we would end up seeing happen is you would have the electron traveling along here very quickly. It would hit something, so it would hit a mercury vapor, and then it would lose a lot of its energy. So what it would do is it would either get stuck to the grid or bounce right back and stick to it here, which means it would not be read by this ammeter here. And that would explain these drops that we're seeing right here and these other places right here. Now, in the case of mercury, we found these values to be 4.9, 6.7, 8.8, and 9.8. So at these spots, we saw these inelastic collisions were occurring. These were the spots where we saw that the energy was transferred from the electron that was moving to the mercury vapor. And what's happening here? What's happening is that we're exciting the electrons in their outer shells. So if you think about your chemistry class for a minute, we have a proton and we have an electron traveling around it. Now, electrons can jump up to a higher state, and that's exactly what was happening here. So when the electron was hitting, what it was causing the electron to do was to jump up to a higher state. Think of the electron in the lowest possible shell where it always wants to be. This is known as the ground state. This here would be considered first excitation. And if it was to jump up, it would go to the second and third and so on. And what happens is when they fall back down, they also release energy, the same levels, in the form of photons. So normally we draw this out with what's known as an energy level diagram. So I'll draw out what this is for mercury. And what you're going to see is that these lines correspond specifically to what we're seeing above. So there's a couple values I want to point out on here. I'm going to point out 4.9. I'm going to put out 6.7. I'm going to put out 8.8. And this is not a typo, I'm going to write 10.4. Now you might be saying to yourself, why aren't you including this 9.8? This is one of the numbers on here. Well, what you'll notice is that the peak with 4.9 and 9.8 look the same. And what would happen is this part right here would be a pattern that you would see repeat over and over as we continue to follow this pathway up. So this is known as the first excitation level. This is the second. This is the third. And this 10.4 we're going to call the ionization level. Now, ionization, you might remember from your chemistry class, that means the electron on the atom has gained so much energy that it's left the atom entirely, which means it's a positively charged atom, making it an ion.